Oh, the popular one. 1440. This equation is based on minute, barrel per day. Okay, this is for liquid capacity, right? Retention time. So if the time instead of minute it becomes hour, can you find the value of that constant instead of 1440? Can you? Yeah, so no problem, right? No problem. You know how to use a chart. Now you know how to read the table, right? That's it. Number 3. And number 4. On treating system, okay, in this thing, the big thing is about emulsion viscosity. I think should be restarted. I did it already. Emulsion viscosity, that is the equation you need. Okay? And the rest is just a terminal velocity equation. Another thing is heater treater. Okay, heater treater. Do you know how to adjust the wear height in the adjustable level? The heater treater has this portion, okay, on the outlet. There has a, you see that hole? That is adjustable that we can move up and down. Okay? So adjustment of this control the oil level in here. Okay, do you know how to do that? This is in one of the oil exam, I think. It's have the oil tank, it's have the tank, it's have water, it's have oil, and it's have gas, and outside it have the adjustable height. And I ask you, okay, this is this much thickness, how much is the height? Do you remember that exam? Or exam? It's just rho GH plus rho GH on the left side equal to rho GH. So it becomes this kind of U2 because most of the time we have equalizing pressure, equalizer line to make this gas the same. So we have oil, water, so rho H times rho plus H times rho equal to H times rho of the right hand side. Too easy, right? Is it? Make sure you can do that. Okay. Heater treater, heat required, how many BTU per hour is that equation, right? And we have another equation for width, and like this one is with water cut, Q total, it will tell you that. The rest is the firebox rating, and is it the direct or indirect heating? Direct or indirect? Direct heating. Okay. Even though this sometimes give you indirect heating chart, but heater treater in general is direct heating method because the heating element touch directly with the test fluid, with the fluid from the. You know how to use this chart? Too easy, right? And that's it for this important thing. Heat loss from the vessel. A little bit too much, I think. Number 5. Storage tank. Do you know what to do to not make people die? This is about safety, right? You say upwind or downwind? Downwind, -1. You dare to, not just -1. So even if it doesn't have H2S, should you stay downwind? No, because you can still die because of the hydrocarbon vapor. Even if it doesn't have H2S, but it has methane. We need oxygen, not methane. If we breathe methane, we will collapse. Okay, and the operator found that I think 7 people died for these things. Stay upwind. Okay. Vapor recovery unit is the name of it. RUVRT, vapor recovery tower, black unit, you know the full name on this picture. You know how to do the tank gauging? You know each equipment is called tip hatch. Another type of tip hatch, that's also tip hatch. This is the tip itself, this is the tape. We have that tape, color cutting, there's a hydrometer. This is in our exam. Tank gauging is just break the reading into several things added together. Too easy. Okay. Another valve, an inline vent valve. Vapor recovery unit, allow me to ask you about, and there's one word that you should be aware of. Deflagration or something. Deflagration is internal frame and you need a frangible roof, fail the bottom part. Okay, that is a keyword for this thing. Number 6. Compressor. Okay, for gas, when calculate compression ratio, everything has to be PSIA. I have seen many of you when we do like determine the number of stage for the vapor recovery unit. You use vapor recovery unit take 4 ounces, right? And 16 ounces equal to 1 pound. So it's actually 0.25 PSIG. So I've seen many people use PSIG, ratio of PSIG. That is straight to 0, okay? Convert it to PSIA first before do any calculation with this compressor. In the compressor topic, you need to know which type is positive displacement, which type is not positive displacement, okay? You need to know the range of K value. K value is more than 1. That's what you should know, right? It's not CP is in general is more than CP is more than 1. All this jargon, the technical term, you need to know what is the meaning of isobaric, isothermal, isentropic, isochoric. And there's another one, isentropic, but we don't use that. It's constant enthalpy. So flow through a shock is constant what? Enthalpy H. Ideal horsepower for compressor is what? Isentropic process, right? Constant S or entropy, that's how it runs. So if you have number over there, like in the previous exam, can you do it? Yes, you can. E sub v. But you have that equation over there. Should you have that? No, you should not have that. I think you should know the physical meaning of this. Volume, I think we don't do calculation on any of this, but volumetric efficiency go up if we have more gap. Okay. If we don't have, you see this gap. If we have more gap, we have less efficiency. If we don't have any gap, it breaks because we don't want it to hit. Okay. I think the mouth is okay. This one, compression ratio. Very like typical kind of question is, hey, we have vapor recovery unit. How many stages do we need? Okay. Provided that the discharge temperature doesn't exceed 275 Fahrenheit, what do? You already know the guideline that compression ratio should be between 3 or 4. It could be 2. Okay. So what do? You test. If you do one stage means n equal to 1. What is the compression ratio? Okay. If you do n equal to 2, what is the compression ratio? If you do n equal to 3, what is compression ratio, right? Once you know those compression ratio, you go to another slide, number 7. Number 7, you can calculate the temperature based on that compression ratio, isn't it? So there's equation, very important equation, I have it separate. So this is, once you get compression ratio, we can calculate the discharge temperature of each stage. Okay. So if you have compression ratio of one stage, compression ratio for one stage, then you get that compression ratio over here, and you have suction temperature, then you can check the discharge temperature. And if it doesn't exceed 275, then we accept it. It may not be 275, it depends on whatever I write in the question statement. Okay. So you've got to be able to tell how many stages of the compressor. Number two, you should be able to tell what is the horsepower of that compressor that we should use. There are two equations for the horsepower. One is a short one, 22 multiplied by number of stage, multiplied by N, multiplied by F, multiplied by QG. Another one is a long version, isentropic horsepower. If you do both, it should go close together. Yes, question.
You said that the 275 will be stated in the problem as our maximum temperature?
It
So it
is.
can apply to every question?
It will say in the exam what is the maximum temperature.
You solved it.
In your exam it doesn't, but in the midterm exam I say that, right? In the O exam I didn't say it, and what happened is I have to write it down in the exam room. Okay, so the temperature that you should not exceed will spell out in the exam. Okay, I may say select the number of stage provided that the discharge temperature at any stage doesn't exceed 280 Fahrenheit or something like that. But the value that you use for TD equal to TS something, that has to be Röntgen. Oh, where is it? This is number 7. This has to be in okay, Röntgen. You don't do that in Fahrenheit. I see some students do it in Fahrenheit. I want he or she to stay with me for the next semester. That has to be Röntgen. And this PD has to be PSI A, not PSI G, okay? If you use PSI, if you get the compression ratio, like if your number of stage is like 9 stage compressor, it's probably wrong, okay? And the reason for that you get 9 stage is because you didn't use PSI A. Alright, the long version for horsepower calculation is this equation. This will be more accurate because this taking into account for the K, the eta, and the E, but the previous equation doesn't really do that. Okay? It doesn't have K, doesn't have eta, doesn't have E, but it should be like close. Okay? It may not be close. What about a compressor? What else is about a compressor? You know how to derive it? What is the assumption used in derive the ideal horsepower? Constant S, right? You know how to draw the diagram for multi-stage compressor. When I say draw the diagram, I mean okay. Can you draw this in the Euler diagram? Of course you know the unit, right? Okay, what kind of unit that you need to know other than S and H? CP, okay? CP, specific heat capacity, okay? That is what you need to know the unit. CP in both SI and what else? Field unit. Thermal conductivity K. You need to know the unit. U value, overall heat transfer coefficient, you need to know the unit. Okay? So A to B is it compression? On nothing. What is it? So A to B, we have compression, right? A to B has compression. When we have compression, do we need this way is constant what? Entropy. S is constant. B to C is what kind of process in B to C? What do we call? Constant pressure, right? We call isobaric. Thank you, Katie. You need to know like where is A, B, C in here and where is that in here. And you know that if you use 2-stage, please have less horsepower, okay? If you use 2-stage and you require more horsepower, then it is wrong. When we add more stage, this horsepower should go down because we cool it, okay? We don't test you on the deliberation, but what do we test you on this? We test you this kind of integration that come out and get your log, right? Integrate of 1 over PdP equal to natural log of P2 over P1. Yes, we test you on that. Mathematics. Why? Because I want you to stay with me. Because I think the product is not ready to be released yet. You cannot do that, okay? Please do that. You may not know it now, but know it on the exam date, okay? Specific heat ratio, the equation to calculate any of that, you need it. So other than this compressor thing, you know how to read the chart, you know how to calculate the horsepower. That's it. Number of stage, just that. The rating ratio, it has to be given. I cannot, oh, okay. This kind of conversion factor is needed for other section too. Okay. 550 pound force foot per second equal to 1 horsepower. 1 BTU equal to that much pound force foot. You need it. Okay. Is the maximum work or something? Review it. Okay. Horsepower. Okay, this is power. Power is it's just a conversion, right? So I think we go through this already. So the thing with pump and compressor, they are similar. For pump, the objective is you know how to calculate horsepower. Do you know how to calculate the horsepower of pump? Yes? How many horsepower of pump do you need? What kind of information do you need to do the pump horsepower? Arif, what kind of information do you need to do the pump horsepower calculation? You need what? Temperature and pressure? I don't think I need that. We need some kind of pressure. We need head pressure or discharge pressure minus suction pressure. So we need to know how much pressure that is boosted by using the pump. Okay? And we need to know the volumetric flow rate. Just those two information is enough to calculate the pump horsepower. Do you know how? Multiply them together. I think that's about the pump. Multiply them together. Okay, the compressor, I hope you know which type is reciprocating compressor, which type is PD, which type is centrifugal. When it's spinning, it doesn't mean that it's centrifugal, okay? When it's spinning, it can be PD type. Okay, review it. Pump video, you need to know which type is diaphragm, what is diaphragm type, is that good at handle solid? Diaphragm is good at solid, is it? Yeah, how does it look like for the vent pump? You should know that. Okay, this is important. PSI 2 feet of liquid. At least you should have that formula. Oh, by the way, PSIA is pound force. Is it pound force or pound mass? Pound force, right? Don't miss that. It's not pound mass per square inch. PSIA is pound force, not pound mass. Don't put pound mass for me. Put the pump in parallel, in series. Read this. Okay, horsepower output. Horsepower output. bhp is Q multiplied by H. So that is, it has to be the correct unit. Okay, brake horsepower, total difference, feet of liquid. Specific gravity divided by that number. In SI, what do we do? In SI, we have what is in SI? I think we have it at the very end about SI thing. Not in here. Okay, maybe some other place. But we know how to calculate horsepower already, right? I think we will go across the equation and have SI. So horsepower, or brake horsepower is flow rate, gallon per minute. Multiplied by head. Head is the differential pressure in the unit of feet. ST, so basically you need that equation, okay? You need that equation. What else? NPSHA, what is the full name for that? NPSHR, what is the full name for that? What happens if NPSHA more than NPSHR? Good thing happens if you flow. If NPSHR more than NPSHA, it doesn't flow. Okay, this elevation thing, I wish you go through it. Okay, it's about calculate. I think we have the equation for like boundary equation for head of the system calculation. So head of the system should equal to the pressure drop, maximum possible pressure drop in the system. Otherwise it doesn't flow. Okay, that's that. Typically, when we do the calculation, we neglect all those things. Vapor pressure, I think we take quite a bit of time to discuss that hot fluid is more difficult to pump, right? Because it has higher vapor pressure. You remember that?
Yes.
Why is that? Is that because it's decreased NPSHA? Let's take a look at the equation. Equation for NPSHA. I don't have it here, do I? Maybe it's in pump 2. Number 8, number 7, pump 2, several kind of pump, reciprocating. Okay, this is diaphragm pump. You got to be able to match pump picture with the name. Okay, match pump picture with the name. And pulsating flow control. You need to know those 3 types, okay? Liquid filled vessel, gas cushion vessel. I think you write it down already. Tune acoustic dampener. We don't do frequency thing, okay? NPSHA, okay. If you have more vapor pressure, see, HVPA, absolute vapor pressure, deposit suction head available go down. So if you heat it up, NPSHA go down based on this equation. Or you should write this down. Okay, you should write this down. Not just the formula, but the unit of each parameter and what it is. You have 8 pages, that's a lot. Write it down. Reciprocating compressor. Okay, this is HA or hydrostatic head available. Okay. Oh no, I'm sorry. Acceleration head. So once you go through this thing, okay, axial is split, radial is split. Is this axial is split? Yes. Radial means it's at the same radius. Okay. Radial is split. What is this thing? Diaphragm. What is that? Rotary lobe. And both of them are PD. None is centrifugal. Centrifugal. What is centrifugal? Centrifugal look like those things. This thing is centrifugal pump. That's centrifugal pump. More centrifugal, that's centrifugal. H pump, I showed the picture during the lecture. Okay, I didn't add it in here, but H pump is just like this, but put in horizontal, it's multi-stage centrifugal pump, multi-stage centrifugal pump. Put the pump in series, increase the pressure, put it in parallel, increase the flow rate. Okay? Pump horsepower. Oh, where's pump horsepower thing? Oh, okay, this page. It is hiding over here, but you need this page. This is a general horsepower calculation. It has several equations, including that 3960. So it has several kind of fitting parameter. Not fitting parameter, but several kind of constant, depending on what unit you have. Okay, and basically you will find out that it is just, if you use everything SI, you don't need conversion factor. Everything SI means Q is cubic meter per second. Okay, head time rho become pressure in Pascal. If you have Pascal and cubic meter per second, you don't need conversion factor. Or even if you don't know that, but you have this page, you can do the conversion, right? Delta P, what is delta P? PSI. What is the formula to convert PSI to Pascal? How many Pascal could 1 PSI? Write that down. 6,894 something, 0.7 maybe. Around 6,900. You Google it, okay? I think I write it down too, somewhere over here in the unit conversion. So you got to be able to convert from PSI to Pascal. Just write the number down. It's just one number. Flow rate, cubic foot per second. Can you convert that cubic foot per second to cubic meter per second? Yes, very easy. Okay. So this page is good because it can do horsepower for every kind of unit. Even if it comes in gallon per minute, oh, use this gallon per minute, and delta P in PSI, oh, hydraulic horsepower is that much. Easy, right? In the pump, you calculate, you have to tell what kind of pump which one to use. If you want high pressure, we use centrifugal pump. No. If we want high pressure, we use PD pump. If we want high flow rate, we use centrifugal pump. Unless you want good flow rate, high flow rate, and also high pressure, use multi-stage centrifugal pump. Okay, like the H pump. You pump it downhole. Radially split, axially split. You know which direction it is. What is self-priming? You know that, right? Self-priming requires. Don't put your. So self-priming pump requires some liquid inside. Okay. Otherwise, it doesn't work. This is about unit conversion. This is a Reynolds number. Oh, this is pressure. You see, I put 1 psi equal to 6,895, about 85. Okay. Inch of mercury. Typically we use inch of mercury when it's become vacuum. Okay, vacuum pressure. Vacuum pressure sometimes is reported in millimeter. Okay, millimeter of mercury. You can copy it from here, okay, but you're not allowed to print it. It has to be your own handwriting, right, in that 8 pages. What's next? Transfer. Metering. Okay, metering. Flange tab. Okay. Pipe tab. You have more error because of roughness in the pipe. C prime has several things. You know how we derive that? What's the assumption that we use? We neglect what? Gravity term, right? The big thing in that is the derivation, we neglect the gravity term. See, that term is gone. So we neglect the gravity term. So any meter run that is not horizontal, is there vertically, that's wrong meter run. You cannot do it like that. So you see the oil exam is talk about pressure 1, 2, 3, and where is highest, where is lowest. You got to know that, right? Highest, lowest, medium, something like that. P1, P3, P2. Okay? When the contractor is what point? Is it this point or that point? So it is, it say over there, when the contractor is over there.
I have a quick question.
Yes.
Why would the pressure have dropped if the flow is expanded back to its original diameter? You have the same rate, the same diameter pipe, and it's back to the original diameter. Why would you have lower pressure?
Because we have restriction. That is restriction.
Right, but at the very end there, all the way off on the right, there's no restriction there, right?
Yeah.
And you're not taking, so why would you have lower pressure there and then you go upstream?
P3, why it is lower than P1?
Oh, because you're losing energy going through the restriction.
Through a small hole, we like pay some energy. It takes some form of energy to change the velocity profile. Okay, the velocity profile shape has to change. It has to squeeze into the small area. So we have pressure drop. I think that's a flow conditioning system, not the dampening device. I think I made I think this is not the dampening device. I changed that during the lecture. Okay, the final equation that you need is that one. Okay, it's that one, and you know what is C prime. Okay, if you need to use it, and then you need this one, right? C prime equal to what? I will tell you FR and all this multiply equal to something, and I give this one table for you to read for F sub V. That's possible. That can be done in 5 minutes actually. Right? So this is a table. I'm going to give you just one table to finish up the right table because I don't have too many space in the exam. So that's all about senior meter. Some of you didn't watch the video, but okay, if you watch the video, Daniel senior fitting means there's a way that we can change the plate while we are flowing. If it is junior fitting, you have to stop the flow. Okay? That's that. What else can be in the exam? Number one factor is the pumper change the refit plate and does not record anything. A.O. Smith meter or several other type of meter. Coriolis flow meter. That's the video that we show it together, right? It's operated by swinging thing and it have a twist out of phase. You remember that? It's not about measure the pressure drop. Orifit is about measure the pressure drop, but Coriolis flow meter is about directly measure the mass. It also tells the density. You remember that video? If you don't, watch it again because the working mechanism of Coriolis flow meter is very likely to be in the exam. Okay? It's not convert from pressure drop to flow rate. It's use out of the swinging motion of the tube inside. The tube inside is vibrate. You need to know that. And in general, which one is more expensive? Coriolis is more expensive, okay, than the refit plate. Water injection facility. There's one calculation in that water injection facility, which is the only calculation is this thing, and it's have solution. So we tell you frac gradient, specific gravity, the depth, high friction, assume 10% or something. This will be spelled out, but okay, you do the one again. Just follow this example, okay? This is solution. From this shot pressure, you go to that minus that and that, okay?
So that's all we need for that.
For the calculation, you need to know the name of. There are several things. Another picture. What is this pump? Triplex pump, right? Triplex. Is it PD or centrifugal? It's PD. You have. What is the name of this diagram? What is the name of this diagram? Stiff diagram. Okay. This is telling about the signature of the composition. Huh? Okay. And you need to know the name when you see this diagram, even though the font size is extremely small. But we may say, okay, common water pattern. I'm really happy that we have that's a stiff diagram. So the practice on this, there's a filter, okay, and there's a multi-stage centrifugal pump, okay, loading, metering, manifold, 100-degree filter, multi-orifice valve. What is this called? Y, okay, is this because it's a Y shape? Strainer, it has a filter. When I show you this, is this compressor or pump? You say none of the above, right? Not much in here, but you put in your senior design, I believe. 11. Oh, where's 11? Okay, this kind of piping, you've got to know how to calculate pressure drop for liquid line. Pressure drop for the liquid line has two cases, laminar or turbulent. If it is laminar, you got to use the right equation. If you use 2F, rho b squared over d, that is fanning friction factor. You got to write all this formula in, okay? 2F rho b squared, rho g sine theta. When we go up, we lose the pressure due to gravity too, okay? When we go down for single phase flow, we gain the pressure due to the hydrostatic head. So if I want to pump from here over the mountain, how much is the pressure drop do I have? Or if I tell you the pressure at point A, how much is the pressure at point B? You got to be able to do that. So friction factor equation, of course, you write it down. Harlan equation, that is the one. Epsilon is the pipe roughness in the centimeter of diameter. Natural log 10 This is fanning friction factor, you write that equation, and this is the top one. 16 over Reynolds number is for, so you have 16 over RE, that's for fanning, not Moody, right? 16 over Reynolds number, and it's for laminar flow, so you have to check Reynolds number if it is above 2100 or not. So this is all, okay? The rest, the possible question that you may have is any of this, because you already have answer and we discussed that in the class. Successive method is not in the exam. Too bad. I think it's easy enough, but okay, we skip that. Isothermal flow, okay, this is about the liquid. What if it is emulsion? If it is emulsion, you treat it like single phase liquid, but you use the emulsion viscosity. Emulsion viscosity is in the emulsion section. Mu M equal to mu C multiplied by 1 minus W, everything to the power of minus 2.5. You remember that? Use that one, we talk about it. Isothermal flow equation, split gas, Weymouth equation, AG isothermal, you need that, okay? And you got to know when to use that, that is at the back. Panhandle beam, mostly we use panhandle beam. And the conclusion remark, okay? This is what we want to review. Putting pipe in parallel, in series, in loop, that is just one equation, right? Or calculate equivalent length, that's just one equation. And it is in the homework too. I think I post all the homework solution and all exam solution. You have all exam solution, right? And you also have all quiz without solution except the last quiz that you have solution posted. Gas treating. Oh, gas treating. There's a lot to write down or memorize. Okay. Whatever you see in the gas plant, select some process. Is this a physical or chemical solvent? Those things you need to know, right? That's question. The question example you should review. Okay. Gas that come from hydrate. Do we do dehydration first or we remove H2S first? That you need to know. We remove H2S first. So gas that is sweet is typically wet. But when we do glycol tower, gas from glycol tower is already sweet. And when it passes a glycol tower, it's still sweet. Okay? It's not sour. We have to remove that first. Review all this, what chemical is what. Oh, this one, amine. Secondary amine, this primary amine. Need to know that. And how do we recover anything? Typically in the glycol contact tower, we regenerate by heat it up. Okay? That's glycol. Same thing is true for amine. What type of amine do we see in the gas plant? Primary amine, only that? I think they use both MDA and DA. Okay, they use both of those. They also use filter, right? And they use select salt process. Krauss process do what? Select salt process do what? You need to know. Krauss process convert everything to that yellow thing, sulfur. Okay, sweetening equation, review it. Within that third equation, it has this because this thing cannot be in, and we have to filter it. This thing cannot be in the calculation section. Flow assurance, we didn't talk much. We talked about hydrate inhibitor. There's methanol. Methanol is a thermodynamic inhibitor. Okay. The rest we talk about serial slacking. We talk a little bit about asphaltene. Basically, that's in your quiz, right? Asphaltene melt. Asphaltene doesn't melt when we heat it up, but wax melt when we heat it up. Asphaltene precipitate in short, okay, like pentane or something. But wax will dissolve. That is. And most of the stuff we skip it, but you can match the picture with the name, right? Naphthalate is naphthalate deposit. Heat transfer is one equation you use. Just that. And you know the unit of each of those things. Physical meaning of Nusselt number, you remember that? Is Nusselt number is a flow property or fluid property? Nusselt number is flow property. Random number is fluid property. Reynolds number is flow property. So Prandtl is fluid, this is flow, and that is flow. Manifest flow is with a shaft. Basically just that. Okay. Any other questions? I think okay. We have two parallel things. Basically, you write 2-3 equations and then the equation is in the box right now. I think that's it. I think you should be able to do it. I mean, get 120 because this. Can you stop it?